Hello everyone, welcome to topic 9.6, coupled reactions. By the end of this, you should be able to explain the relationship between external sources of energy or coupled reactions and their ability to drive thermodynamically unfavorable processes. So when a reaction is thermodynamically unfavorable, there are ways to force the reaction to occur. If you have to charge a battery or power an electrolytic cell, which we're going to discuss in 9.10, one way to do this is to use an external source of energy, such as a power supply, to provide the energy needed to overcome the unfavorable positive gives free energy. In photosynthesis, light is used to provide the energy to convert carbon dioxide and water into glucose in photosynthesis. That is also unfavorable. Light and electrical energy are two examples of external energy sources that can be used to drive reactions forward that are normally unfavorable. Another way to drive a thermodynamically unfavorable reaction is to couple it to a reaction that is thermodynamically favorable. The negative delta G from the thermodynamically favorable reaction provides the energy needed by the unfavorable reaction and drives it to proceed. This is sometimes referred to as a coupled system. Overall, the delta G for the coupled reaction is negative, therefore it is favorable. In a coupled system, the individual reactions share common intermediates, so one produces and then it's used by the other. For example, the process to extract zinc from zinc sulfide is unfavorable, so this one is unfavorable. However, we can couple, extract zinc, this one. So this one's unfavorable. We see that with the positive delta G. Okay, it can be coupled though with another one that's going to use this bit up so that it proceeds forward, and thus it has a larger negative delta G. So the delta G for the coupled reaction is the sum of the individual reactions. So remember we talked about how we could do this for delta H's. Because they are state functions, we can do this with delta G and delta S as well. This is also true in biological systems. Coupling a thermodynamically favorable process or reaction with one that is unfavorable will drive the unfavorable reaction to proceed. So we are going to, in this I do, write the overall reaction and then determine if that reaction would be an example of a good example of a coupled reaction. So by good example, they mean, is our delta G going to be negative? Right, because we would only want to couple a reaction to make it favorable. So what is our overall reaction? Okay, so we're going to cancel out our intermediates. So this is just similar to other processes where we're looking at the sum of reactions, except we don't have to multiply it by anything. Whoop, whoop. So A2B3 plus CS yields A2C solid plus 3Bs. Okay, so now that we've summed this, so this is our overall reaction, we need to figure out our delta G of reaction, and that's going to be the sum of the two delta G's for the individual reaction. So 150 kilojoules, and since we added, we're going to add these, plus a negative 120 kilojoules. And when we add these together, we see we still have a positive 30 kilojoules. So no, this is not a good example. It is still unfavorable. Okay, so now we're going to look at the we do. So here we go. Oops, too far. So given the following reaction for extracting silver from silver ore, is this a thermodynamically favorable reaction? What do you think? Write it down. You should have picked no. And the reason for that being is that our delta G is positive, which tells us that it is thermodynamically unfavorable. Well, what if we couple this reaction with this following reaction? Would the coupled reactions be favorable? Show the overall reaction and calculate the delta G to support your answer. Well, I'm going to multiply this by 2 to get rid of this fraction. So I'm going to multiply this one by 2. And that also means that this is now 1, and so a reactant oxygen and a product oxygen cancel. And so I write what I have left. So this is a 2, and this is a 2. So 2 Ag2O solid plus 2 carbons yields 4 silver and 2 carbon monoxides. Okay, so now we're going to figure out this delta G of this reaction. So we're going to add them together. So 21.9 kilojoules plus 2 times negative 137.3 kilojoules, because we multiplied the reaction by 2. And we should get negative 252.7 kilojoules for this. Okay, so that completes the examples for section 9.6. I want you to work on the you-dos, check your work, and thank you for tuning in.